According to National Electrical Code Section 344.10b, metal conduit shall be galvanized or otherwise suitably protected against corrosion. In addition, National Electrical Code Section 300.6c states that galvanized rigid metal conduit shall be suitable for use in concrete. The galvanizing process creates a protective zinc layer on the conduit. This zinc corrodes instead of the underlying steel. This provides long-term protection against corrosion in most environments, including concrete. The typical practice for rigid metal conduit embedded in concrete varies, but there are several common options. Firstly, embed the conduit as is. Galvanized rigid metal conduit is embedded in concrete without any additional coating. This is the most common practice, as it is typically sufficient for most environments. Secondly, wrap with anti-corrosion tape. A self-fusing or butyl rubber tape is wrapped around the conduit before embedding it in concrete. This provides additional protection against corrosion in harsh environments such as areas with high moisture or salt content. Thirdly, apply a corrosion-resistant coating. A liquid or powder coating is applied to the conduit before embedding it in concrete. This provides a thick, protective layer that is resistant to corrosion and can be used in extreme environments. The decision of whether or not to use an anti-corrosion wrapping on galvanized rigid metal conduits in a concrete duct bank depends on the specific environmental conditions. If the concrete is likely to be exposed to moisture, salt, or other corrosive substances, it is advisable to use an anti-corrosion wrapping to provide additional protection. However, if the concrete is in a dry and protected environment, galvanizing alone may be sufficient. It is always important to consult with the local authority having jurisdiction for specific requirements in your area, as they may have additional rules or recommendations regarding the protection of conduits in concrete duct banks. Regarding the protection of metal conduits in concrete, the National Electrical Code provides guidelines, but local interpretations and environmental factors play a crucial role in determining the appropriate level of protection. Galvanization, as mentioned in National Electrical Code Section 344.10b and 300.6c, is a widely accepted method for corrosion protection. The zinc coating acts as a sacrificial layer, corroding before the steel conduit itself. This process, known as galvanic protection, is effective in many common environments. However, the effectiveness of galvanization can be compromised under certain conditions. High levels of moisture, especially when combined with chlorides or other corrosive agents, can accelerate the corrosion of zinc. Similarly, variations in concrete mix, such as high alkalinity, can also impact the long-term performance of galvanized conduit. For installations where these factors are present, additional protective measures are often recommended. Anti-corrosion tape, typically a self-fusing or butyl rubber compound, provides a barrier between the conduit and the surrounding concrete. This barrier prevents direct contact with moisture and corrosive elements, extending the lifespan of the conduit. The application of anti-corrosion tape requires careful attention to detail. The tape should be applied in overlapping layers, ensuring complete coverage of the conduit surface. Any gaps or voids can become points of vulnerability, allowing corrosion to initiate. Surface preparation is also essential. The conduit should be clean and free of any loose debris or contaminants that could interfere with the adhesion of the tape. Another option for enhancing corrosion protection is the application of a corrosion-resistant coating. These coatings, available in liquid or powder form, create a durable barrier that is highly resistant to chemical attack. The selection of an appropriate coating depends on the specific environmental conditions and the type of concrete being used. Epoxy coatings, for example, are known for their excellent chemical resistance and are often used in harsh industrial environments. Powder coatings, applied through electrostatic spraying and then cured with heat, provide a uniform and durable finish. When specifying corrosion-resistant coatings, it is important to consider factors such as adhesion, flexibility, and impact resistance. The coating should be able to withstand the stresses of installation and the long-term expansion and contraction of the concrete. Furthermore, the coating should be compatible with the galvanized surface of the conduit. In some cases, a primer may be required to ensure proper adhesion. In addition to these methods, cathodic protection can be used to mitigate corrosion in underground or submerged concrete structures. Cathodic protection involves the use of a sacrificial anode or an impressed current system to shift the electrochemical potential of the conduit, preventing corrosion from occurring. This technique is typically employed in critical infrastructure projects where long-term reliability is paramount. It is also worth noting that the quality of the concrete itself can play a significant role in the corrosion of embedded metal conduits. High-quality concrete, with low permeability and proper curing, can provide a dense and protective environment. The use of corrosion-inhibiting admixtures in the concrete mix can further enhance its resistance to corrosive attack. These admixtures work by forming a protective layer on the surface of the embedded metal, preventing the ingress of chloride ions and other corrosive agents. The selection of the appropriate protective measures for rigid metal conduits in concrete should be based on a thorough assessment of the environmental conditions, the expected service life of the installation, and any applicable codes and standards. Consulting with a qualified corrosion engineer or electrical inspector can help ensure that the chosen methods are effective and compliant with local regulations. Remember to always consult with the local authority having jurisdiction for specific requirements in your area, as they may have additional rules or recommendations regarding the protection of conduits and concrete duct banks. Considerations for rigid metal conduits or RMC in concrete encompass several critical aspects. The primary concern is corrosion prevention, as concrete can create a potentially corrosive environment for metals. While galvanized RMC offers inherent protection, certain conditions may necessitate additional measures. Firstly, understanding the concrete composition is essential. Concrete's alkalinity, due to the presence of calcium hydroxide, can initially provide a passivating effect on the galvanized coating. However, over time, this high alkalinity can lead to the breakdown of the zinc layer, especially if moisture is present. Secondly, environmental factors significantly influence corrosion rates. Exposure to chlorides, sulfates, and other aggressive chemicals commonly found in coastal areas or industrial settings accelerates corrosion. Similarly, fluctuating moisture levels promote corrosion by creating an electrolytic environment. Thirdly, installation practices play a crucial role. Proper spacing and support of the conduit within the concrete are necessary to prevent stress and potential damage to the protective coating. Direct contact with dissimilar metals should be avoided to prevent galvanic corrosion. The National Electrical Code, or NEC, provides guidelines for the installation of RMC in concrete, but it is not exhaustive in addressing corrosion protection. National Electrical Code Section 344.10b mandates that metal conduits be galvanized or otherwise suitably protected against corrosion. National Electrical Code Section 300.6c specifically allows galvanized RMC to be used in concrete. However, these sections do not provide specific details on when additional protection is required. Therefore, engineering judgment and local codes must be considered. To mitigate corrosion risks, several strategies can be employed. Firstly, barrier protection methods isolate the RMC from the corrosive environment. These include wrapping the conduit with specialized tapes designed for underground applications. These tapes typically consist of a polyethylene or PVC backing coated with a rubber-based adhesive. They provide a physical barrier against moisture and chemicals. Secondly, coating systems provide a more robust form of protection. Epoxy coatings, for example, offer excellent resistance to a wide range of chemicals. These coatings are typically applied in multiple layers to ensure complete coverage. Prior to applying any coating, thorough surface preparation is essential. The RMC must be cleaned and free of any rust, scale, or other contaminants. Thirdly, cathodic protection methods are employed in more aggressive environments. Sacrificial anodes, typically made of zinc or magnesium, are electrically connected to the RMC. These anodes corrode preferentially, protecting the conduit from corrosion. Another form of cathodic protection involves impressed current systems. These systems use an external power source to drive current through the soil, neutralizing corrosion currents. When specifying RMC in concrete, several factors must be considered. The size and type of conduit must be selected based on the electrical load requirements in the National Electrical Code. The type of concrete must be specified, taking into account its compressive strength, permeability, and chemical resistance. The need for additional corrosion protection measures must be evaluated based on the environmental conditions and the desired service life. Detailed installation specifications must be provided to ensure that the RMC is properly installed and protected. Regular inspections and maintenance are necessary to identify and address any signs of corrosion. These inspections should include visual examination of the conduit, as well as electrical testing to assess its integrity. In addition to the above considerations, proper grounding practices are essential for the safe and reliable operation of electrical systems installed in concrete. The grounding system must be designed to provide a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. The grounding conductor must be sized and installed in accordance with the National Electrical Code. Connections to the RMC must be made using approved fittings and connectors. The grounding system must be regularly inspected and tested to ensure its effectiveness. By carefully considering all of these factors, engineers and installers can ensure that RMC in concrete provides a safe, reliable, and long-lasting electrical infrastructure. The key to success lies in a thorough understanding of the corrosive environment, the proper selection of materials, and the implementation of best practices for installation and maintenance. Lastly, the information provided does not take the place of formal engineering training. Always consult with a qualified professional. To summarize, when addressing the use of rigid metal conduit in concrete, several factors need careful consideration. The decision to apply additional anti-corrosion measures beyond the inherent galvanization depends heavily on the specific environmental conditions. Areas with high moisture levels, exposure to chlorides like those found near coastal regions, or the presence of other corrosive agents warrant extra protection. Options include wrapping the conduit with specialized anti-corrosion tapes, applying robust epoxy coatings, or in extreme cases, implementing cathodic protection systems. The National Electrical Code allows for the use of galvanized rigid metal conduit in concrete, as stated in sections 344.10b and 300.6c. However, it is not a one-size-fits-all solution. The engineer must assess the environment and decide what is needed. Proper installation is also crucial. Ensuring adequate spacing and support of the conduit within the concrete prevents stress and potential damage to the protective coatings. Also, avoiding direct contact with dissimilar metals prevents galvanic corrosion. Regular inspections are essential to catch early signs of corrosion. Also, be sure to consult local authorities for specific requirements, as they may have additional rules or recommendations. Remember, the quality of the concrete itself contributes to the protection of the conduit. High-quality, low-permeability concrete can provide a more protective environment than lower-quality mixes. Finally, proper grounding practices are vital for safety. A well-designed grounding system provides a low-impedance path for fault currents, minimizing electrical hazards.